I'm not surprised at the incredible computing power that's available in the physical universe. I remember, back learning quantum field theory at Harvard more than 30 years ago. They told us, well, at every point in space-time, there was an operator, an infinite dimension matrix. And these were propagated through time with a set of equations that are called the Standard Model. And just when you think about the incredible computing power that happens in the universe, it's not surprising that there's power out there. What I am blown away with is the fact that over the last 30 years, we have found ways to tap into that computing power, and that these, it's really impressive. I was also very interested in the claim that you can actually preserve quantum coherence at room temperature, which is something I want to follow up with, because that means that there may be a possibility of actually having quantum computers in your cell phone. Whereas previously, the scenario people were looking at were giant supercomputer front ends to small boxes with cryogenics in it to provide cloud-based access. So that we may actually, if that is actually true, that could change, the way we actually deploy this. Now, let's see, one of the bright spots of bipartisan agreement on this committee and in Congress is about robust funding for exascale computing. And so, Dr. Binkley, could you discuss how the next generation exascale computing system, such as the one at Argonne National Lab is working to bring online in 2021, could synergize and elevate a robust quantum computing technology ecosystem?
Yeah, I can cite a couple of examples of where that occurs. One is that obviously there's a tremendous search for quantum materials that can be used in qubit technologies. And so a lot of the simulation capabilities that exist in our material science and chemical sciences communities can be brought to bear on that problem. Another area that is under active exploration is that you can simulate quantum computers on classical computers. And in fact, with the largest computers we have today, we can simulate quantum computers that contain up to about 40 or so qubits. And that actually gives us a way to begin to simulate algorithms and do algorithm development. And that will be accelerated when we go to the exascale class computing. Also, the exascale computing is giving us the ability to look deeper into particle physics and nuclear physics phenomena, and that'll give us insights on quantum algorithms that can be developed in those areas as well.
Thank you. And I guess on the next panel of witnesses, we're going to see some discussion of what the key skills that you need to get the workforce that can actually do this. And I guess the list that appeared in the written testimony were cryogenics, FPGA programming, superconducting materials development, and microwave engineering. That sounds pretty much like a description of what I did during my 25 years at Fermi National Accelerator Lab. I think I have somewhere on my laptop back home are hundreds of pages of FPGA code, cryogenic systems calculations, designs of high-power phase shifters for microwave applications, and so on. And so it strikes me that the national labs are really well positioned to play a key role here. And so I guess a question for Dr. Binkley again, how exactly is the Department of Energy using the capabilities of Argonne Lab and Fermi Lab to advance quantum science to hopefully stay ahead of the competition here?
So that's a very good question. And so presently, we're really at the very beginning of that process. And as I mentioned a little bit earlier, the first step is to develop and deploy a few testbed computer systems at various of our national laboratories so that researchers can begin to do systematic development of algorithms and computational approaches to problems. And then, later on, depending on where the field of quantum computing goes, there may be opportunities where DOE technologies can be applied in that path as well. But right now, our focus is really on the very, very early stage development of quantum computing algorithms using testbeds, and also looking at quantum simulation as a technique for looking at molecular problems.
Thank you. And I guess my last question is for Dr. Caruso and Dr. Williams. There's two big areas, it seems to me, one of which is the whole encryption and, and communication. The other one is just using this as a compute engine for things like, protein folding and all these really intractable problems that we're facing. And so how do you see, in one of these areas, it's probably okay to have open communications with the entire world. The other one, just for national defense reasons, has to be very closely held. And so how do you handle the communications between, the dark side that has to remain dark and, the purely scientific side that maybe shouldn't?
Well, it's a great question. I'd say that the National Science Foundation funds open, basic, fundamental scientific research. And so if you were to look at sort of pre-quantum encryption algorithms, there's NSF funding involved in that, and other agencies are involved when you talk about sort of in the classified space. There are other opportunities there, but at the National Science Foundation, the work funded is open.
And do you feel there's adequate communication, or is that just a problem you run into all the time?
Excuse me, communication among
Oh, between, for
researchers,
example,
or-
do your scientists that work, in the unclassified scientific area, you have good visibility into the technologies that are being developed with the non-trivial amounts of money we're putting into the classified sector? Or is that a problem where you end up inventing, the same device in two different spaces with a lot of inefficiency there?
Golly, given I don't have a clearance, it's a little bit hard for me to comment on both sides at the same
Okay.
time. Maybe I could just, if I could take 20 seconds and just to tell you a story that during World War II, some of the fundamentals behind RSA encryption were done in the dark at the same time as in England. And it was really shocking to imagine that 2,000 years of how we were doing encryption was turned on its head by RSA and the algorithms there. And yet, unbeknownst to the team here in the United States, there was another team in England doing the same thing. And so sometimes there are ideas that are in the area, really, really smart people put together these ideas and can come up with not exactly the same, but some really similar, super, super creative ideas.
Okay, I guess I've exceeded my time limit here.
Thank you. And I now recognize Mr. Byer for 5 minutes.
Thank you, Madam Chair.